Hello everyone. Today let's solve the problem nuclear fission, right? Fusion basically, sorry. So this was asked in the Codeforces beta round 65 for the division 2, right? So you can just go through the question. This is somewhat lengthier and somewhat code will be difficult to understand. So we have to go step by step, right? So we'll be making use of the DP as we are solving the problems on the bitmask DP. So we'll be making use of the DP. So and we will break down the problem in such a way that we understand everything, right? I mean every step, right? Step by step. Uh, in simple terms, right? So you can just go through the question. I'll just summarize the question so that it will be easier for us to solve the problem. So this is 2200. Okay, this is fine. This is hard, man. Actually, let's go with the question first, right? Let me summarize the question so that it will be easier for us to solve the problem. Just give me a second here. 1 second, man. So I'll just choose this thing. This is fine. Now we have n atoms, right? So what we have here, we have n atoms, right? And we may fuse any two atoms repeatedly, right? So what we can do here, we may fuse any two atoms, this one, repeatedly, right? So just keep this in mind. Fusing any two atoms repeatedly in the sense we can sum their atomic numbers, right? So we have to know the atomic numbers, right? So we can sum their atomic numbers, right? So again, I'll just we have to move to the chemistry part here. So this is fine. We have n atoms and we may fuse any two atoms repeatedly, right? So nothing but here we may sum their atomic numbers, right? So but never split. We should never split, right? What is our main goal here? We have to obtain exactly k targets. What we need to obtain here, we have to obtain exactly k target atoms. So k target atoms, just remember this one. What is our main goal here? So we have to obtain exactly k target atoms whose total sum equals initial sum, whose uh, total sum equals initial sum. Just remember this one. This is our main goal basically, right? So again, I'll just read out this one. Just listen to this one carefully. We have n atoms, right? And we may fuse any two atoms repeatedly. In the sense, we can sum their atomic numbers, but we should never split them, right? So we should never split them. What is our goal? Our goal is to obtain exactly k target atoms, nothing but the symbols whose total sum equals initial sum. Right, so this is simple, very simple. Right, let's move on with the next one. So each original atom must be exactly once in some equation of the form, that is a plus b plus this thing to target. So each original atom must be used exactly once. Just remember this one, right? In some equation of the form, this one, equation of the form a plus b plus this one up to this one, what do we call target basically, right? So again, let me repeat this one. This is important. Each original atom must be used exactly once. Each original atom must be used exactly once in some equation of the form, this one, a plus b up to the target, right? So we have to decide if possible and print one valid partition of the original atom, right? So what we need to do here, we have to decide if it is possible and we have to print if it is possible or not and print one valid partition. What we need to do here, print one valid partition, part I'll just write here, right? So one valid part of the original atoms into k groups, right? So just remember this one, into k groups. Simple, right? So we have to decide if it is possible and we have to print one valid partition of the original atoms into the k groups where each group sum is equal to the target atom number. Each group sum is equivalent to target atom number. I'll just write here TAN, target atom number. Each, again, each group sum is equivalent to the target atom number. Just we have to just keep the sum mind, right? So this is fine, man. Simple. Again, I'll just read out the question loud. Just listen to this carefully. So we have n atoms. This part we have n atoms, and we may fuse any two atoms repeatedly. We know this one, right? We can sum their atomic numbers, but we should never split. I have stressed this one multiple times. What is our main goal? We have to obtain exactly k target atoms. This part we have to target. We have to this one obtain exactly k target atoms, nothing but the symbols whose total sum equivalent to the initial sum. This one, total sum equivalent to the initial sum. I'll write one more equals here, equals to the value, right? This one, comparison operator. So whose total sum is equivalent to the initial sum. So now each original atom must be used exactly once. This we know, this is very important. Each original atom must be exactly used exactly once in some equation of the form a plus b plus up to this one target, right? So we have to decide whether it is possible, and we have to print one valid partition of the original atoms into k groups where each group sum is equivalent to a target atom number. This part, right? So where this one each group sum equivalent to the target atom number, this we have to check. This is fine, simple, very simple, right? So this is it for the question. Basically, let's come to the input output part, man. Let's come to the input output part here. So just give me a second here, 1 second. So here we have n equals 10 and k equals 3. You can clearly see here input output part. So this is nothing but n, and this 3 is nothing but the k. We know this one, right? So we have understood the question clearly, right? So this is fine. You can count this one. We'll be having 10 and we have 10, right? So this will be 10 basically, right? So this is fine, man. Now we have 3, k equals 3, right? So this is 3, this is nothing but the k basically. So this will be, k will be quite obviously 3. The output that we need to get here is s along with the this one, right? So this is fine. Hmm, just give me a second here. Basically what we need to find here, 1 second. This one, we have to diffuse any two atoms repeatedly, nothing but the we have to sum their atomic numbers, but we have to never split, right? So this is fine. So here we have to obtain the exactly k target atoms, right? So we have to obtain exactly k target, means here in this case it has to be 3. So this is possible. See here, m1 plus c plus k, co plus zn plus sc, li plus mg plus this one p plus f. This is nothing but y, sn, pt and y. So we have to obtain exactly k target atoms, nothing but 3 we got here, right? Sn, pt, y, right? Nothing but the symbols whose total sum is equivalent to the initial sum. Here in this case its total sum is equivalent to the initial sum, right? So here in this case we have to return s along with the 3, these 3, right? So let's discuss this thing in detail on the approach. Now for now let's just see the input output. Same thing goes with this one as well. This is n and k. So this is nothing but this one 2 we have, right? Atom. So here this is fine. This is nothing but the atoms. So here this is also fine. Output that we need to get here is s and this one. For the third one it is not possible, so no, right? So this is fine, man. I hope the question part is completely clear along with the this one input output part. Now let's consider this first example. I insist you to try out in the same way for the second example, right? So this one is easy, man, comparatively to the first one, right? You don't have to worry that much for the second one. So I'll just explain by considering I'll just explain the approach by considering the first input. So I can just uh, do the implement the same thing for the example, this one second example, or the input 2 that is given in the question, right? So let's consider this one, meaning so let's discuss the approach followed by the complexities and then let's write the code, right? So this is important, right? First thing I want to tell you here is before getting into the approach part, let me tell you what we will be doing, right? First of all, we will be making use of the bitmask dp here. Just remember, so we will be going with the dp, right? So dynamic programming along with this one bitmask, right? So this will be very helpful. Basically masking will be very helpful, that we will be discussing within the approach. Just remember this one, that we'll be going with a bitmask dp. Also we'll be going with the pre-computing values as well. Let's see that one in the action within the approach. So first thing, before the approach, let me tell you some of the important points what we'll be doing, and then let's consider the first example for the approach, and then I'll just explain how we will implement that one in the form of code, right? So this is fine, man. First we will convert the symbols, man, right? So whatever the symbols that we have, we will convert the symbols. Meaning here, converting symbols in the sense we will be going with the numbers, right? So we can, accordingly with the question, we have to sum up their atomic numbers, right? We have to sum up their atomic numbers, right? So first what we will do, we will convert the symbols, meaning numbers. Then what we will do, we will sort the targets, right? So we will be sorting the targets basically, right? And then finally, this one, pre-compute all the subset sum, right? So I'll just go with here pre-comp, right? So then we will pre-compute all subset sums. So this is the first part. First part, again, just remember, try to remember this one, right? You can just pause the video and look into it basically. If you get confused in the future, you can just come here and you can just look into the steps, right? So first what we'll be doing here, we will be converting the symbols. When I say convert symbols, we will be going with the numbers, meaning we have to sum up their this one, sum their, what do we call, atomic numbers, right? So then sort the targets and pre-compute all the subset sums. This is fine. As I have said, we'll be making use of the bit mask DP, right? So we will be going with a bit mask DP. So I'll just write here BM, nothing but the bit mask DP here. This is fine. Now, what we'll be going with here is, we will be going with a DP of R and mask, right? So DP of, I can just represent on this way, man. So I'll just represent this one on this way. We will be understanding this one in the depth while we consider the first example and discuss the approach, right? So this is fine. So we will be going with a DP of R and mask. When I say DP of R and mask, so this is equivalent to nothing but it can form first R targets leaving mask atoms, right? Nothing but it can form first R targets leaving mask atoms, transition by removing any subset whose sum equals the current target, right? So just remember this one. So we'll be making use of the bitmask DP, and we'll be going with the DP of R mask, that is equivalent to the this one. It can form first R targets leaving the mask atoms, right? So this is fine. Next, third one here, so we will be going with the this one if condition in the sense. So here if DP of K0 is true, meaning here if DP of this one K and this one 0, if it is true, right? So if DP of K0 is true, then what we need to do, we have to reconstruct each target from the stored parent. So I'll just write here reconstruction. If DP of K0 is true, then we will be going with a reconstruction. Just remember, try to remember this part, right? So if DP of K0 is true, we will reconstruct each target from stored parent subsets and we will be printing the equations, right? Else we will print a big no here. So in the third input we have got no, right? Else um, uh, what we'll be doing, if TP of K0 true, reconstruction, nothing but we'll be reconstructing the each target from stored parent subsets and we will be printing the equations. Else we'll be printing big no here, right? So this is fine. I hope this part is clear, man. These three steps basically we'll be doing. So this is lengthier. So let's consider this first example, basically this one, first input, and let's see that one in the action within the approach. Let's try to do that. Just give me a second. Let me delete this one. These three steps we will be discussing in completely detail. This you have to know. That is the reason I said this one. This is fine. Now let's discuss the approach in depth or detail by considering this first example, right? As usual, let's discuss the approach first. So here I'll be considering the first example as I've said. So this is nothing but the n, man. This is nothing but the k. N on the sense, in the question we know already, right? So we have n atoms, right? N atoms, and k is nothing but the k target atoms. N atoms in the sense we may fuse any two atoms repeatedly, right? So but we shouldn't split, that they have given, and our goal we know. We have to obtain exactly k target atoms, right? Nothing but the symbols whose total sum equals initial sum. That's what we need to do. So this is the n, this is k. See here, this is total, we have 10, and this is nothing but 3, right? So this is fine. We have already discussed this one. The output that we need to get here is this one. So one more thing I want to tell you is the output that we need to get here is this one. 3 basically, right? So output basically what we need to get. So we have to obtain the k target atoms whose total sum equals initial sum. This is nowhere written that we have to get this output itself. This can have the multiple outputs, right? So this can have the multiple outputs as well, right? So just try to remember this one, man. We can have multiple outputs as well. So here in this case, the output that we need to get here is this one. So let's see what output we can derive into, right? So let's check the same thing, right? So it can have the multiple outputs as well. Just try to remember this one, right? So this is fine. Now let's move on with the first this one step. So we have been given elements, nothing but the symbol by their symbols, right? So I really don't remember what is this, what is this. Literally, I have to go through the chemistry part again. So which I don't want to know. So I'll just go with the symbols. I'll just read out the symbols itself rather than this one elements, right? So this is fine. First step is we have to map the symbols, nothing but based on their atomic numbers using the element table in the code, right? So this one Mn, so this is 25, Co is nothing but 27, Li this one will be mapping this one. We'll be considering all the this one elements basically, right? First thing, so this is fine. I hope this is fine. This is nothing but elements along with their symbols along with their atomic numbers basically. We are mapping what do we call, we are mapping the symbols to their atomic numbers here. Mn25, Co27, so on up to y equals 39. Simple, very simple. This is the first step, man, right? So let's move on with the second step now, right? So I hope the first step is clear, right? So let's break down this one step by step so that we understand this problem. So this is rated to 2200. Quite obviously that this is the hard problem to implement, right? So let's try to break down and try to understand, right, rather than skipping this these kind of problems, right? So we don't have to solve only 1700 and below problems or 1500 and below problems. Some problems we can easily solve about 2000 or this one 2200 as well, right? So all we have to do is understand this one step by step, right? So let's try to solve this one, right? So next step what we'll do, we will sort the arrays, right? So we will be sorting the arrays. If you remember first what I said, so first three steps, we'll be only going with the three steps. So I broke down that one correctly and I explained, right? That is the reason I explained at that time in the beginning, right? If you remember, you can just go to the video and you can just check those three steps, right? So this one here we have to sort the arrays. Sort the array in the sense code sorts initial atoms S1 and targets S2. Simple. So here sorted S1 is nothing but we will be going with the index value symbol, right? Index value symbol. So this is index. So the 1 to 10, whatever, 1 to 9, whatever I have written. So here first 0, 3 and Li. So whatever I have written. So this is nothing but index. So 3 is nothing but value here, val I'll be writing, and this is nothing but the symbol, right? Same goes with all the things 1 to 9, right? So this is sorted S1. So this is sorted S1. So we have to sort S2 as well. See here, sorted arrays code sorts initial atoms S1 and targets S2, right? So sorted S2 is nothing but 39, y 39, 50 and 78, basically y, sn and pt, right? So this is fine. I hope this one is clear, right? I hope this part is completely clear. Now we have got the sorted S1 and sorted S2. We have successfully sorted this one. Clear? First step is clear. I hope the first step and the second step is completely clear, right? So we are going with index value and symbol for the S1 and S2, the same thing, right? So this is fine, I guess. So this is nothing but the target S2, right? So this is fine, man. Accordingly with the input we are going, right? So I can just check the input. So this is fine. Now let's clearly move on with the third step, right? So let's go step by step. So first what we will be doing here, as I have said, we will be going with a bit mask, right? So we will be masking certain value just to keep or this one modify or update. So we will be masking here. We'll be going with a bit mask DP as I have said earlier. So full mask and subset sums. Full mask in the sense we will be going with a one left shift 10 minus 1. That is nothing but here in this case it will be 1023 value. You can just check one left shift 10. So we'll be making use of this is nothing but 1023. right? So we will be going with a subsum of mask pre-computed for every subnet mask. This we'll see later. So for now, just remember this one, this part, full mask. So this one, this is fine. And subsum of mask, this one will be pre-computed for every subnet mask, right? So this is fine, man. Now let's come to the DP base, right? So this is third part is completely finished. Now let's come to the DP base. So here we have got 1023 full mask, right? So one this one left shift and whatever I have written here minus 1. So this one will be 1024 minus 1, nothing but 1023. So here in this case we will be going with the DP base. Initially this will be 0 and this one full mask nothing but 1023 the value, right? So this one will be true minus before making any targets all atoms remain, right? So before making any targets, all the atoms remain. Just try to remember this one, right? True minus before making. So this one, sorry, this one, let me, I am calling this one minus from that time. So true, nothing but before making any targets, all the atoms remain. So this one will be true basically. DP of 0, 1023. Sorry for calling this one minus 1. This is fine. Now dp of 01023 is this one true is set to true. We know this one. First four this one four steps. I think this is clear, man. Right? Let's move on with the fifth step now. So currently, let's start with the initial one. So when r equals 0, right? So target we have as first this one sorted s2, right? Sorted s2. You can just check first value we have initially. You can just go this one. Go to the video where we have the first this one 39y, right? So we are considering this one 39 by these sorted s2, I mean this one so 39 by 50 sm this one element symbols. So this one 78 pt. First we have to consider 39 by, right? So here r equals 0, target is nothing but 39y. So we have to search the subsets of mask 1023. So this one we have explained, we know how what is this 1023, right? So this is fine. Now we have found the subset of the indices 0 to 34, right? So this one values is nothing but 3 9 12 plus 15. This how we got this one. Just give me a second here. uh, so we have to go with r equals 0, r equals 1, r equals 2, right? So this one is nothing but subset, this one sorted s2 values based on the atoms, right? So based on the atoms or based on the element symbols along with their atomic numbers, right? So first here we have 39 by, so we have found the subset of indices 0 2 3 4 in the sense values will be 3 plus 9 plus 12 plus 15, right? So values are 3 plus 9 plus 12 plus 15, right? So now these basically these correspond to what elements? So this one Li, F, Mg as well as the P, right? So with the atomic numbers, this one 3, 9, 12 as well as the 15. So values we have got here 39. This is fine. Now we will be going with the next mask, nothing but 1023 XOR 29. So you can just check this one. 10 this one, what do we call? We'll be going with the net. Did I skip something here? Just give me a second here. Eh? Yeah, this one also. This one we didn't consider at all. We considered this one for the 39. Subnet mask we didn't consider at all, right? Subnet mask we have to consider. This one left shift 0. Same goes with 2 3 as well as the 4. 0 2 3 4 we have this one subnet of the subset of indices. So we have found the subset of indices 0 2 3 4, right? So we have to go with 0 2 3 4 here. So one this one left shift 0, same goes with this one 0 2 3 4, meaning 2 3 and 4. One left shift 3, one left shift 4. This one is fine. So the values that we get here is 1 4 8 and 16. That will lead to 29. So here we got 39 and 29, man, right? So this is fine. Now we will be going with the next mask, nothing but 1023 XOR 29. So this value we get is 994. I'll not explain how we got this value. We are going with the XOR here. This is fine. So we will set DP of 1994 to true, right? So what we'll be doing, we will be setting one a DP of 1994 to true. Quite obviously we'll be setting that one to true, and parent of this one 1994 is 29. So here we got 29, right? So this one basically. Uh, from the subset of indices 0, 2, 3, 4, when we went with a subnet mask sub, and nothing but sub here, we are going with a subnet mask, right? So this one, what do we call? Sorry, why am I calling this one subnet mask? Sorry, this one is subset mask sub. This one is fine 0, 2, 3, 4 payment. So the values we have here is 1, 4, 8, 16, 29. So this is fine. Now parent of 1, 994 will be 29. So this is for r equals 0. Same thing that we'll be doing for r equals 1 and r equals 2, right? So for the second one, if we remember what we have here, this one, not this one, just give me a second here, 50 SN and 78 PT here. 50 and 78 we have to consider along with the SN and PT, right? So let me come here. Yeah. So target we have 50 SN, right? So here we will be examining the states along with the DP of one mask. Same thing, exactly what we did here. From mask 994, so we got 994 here. This is fine. 1023, this one XOR 29. So we got this one 994 from mask equals 994. We have found the subset this one 159. We have found the subsets 157, sorry. So when I say from mask 994 we have found the subset 157, I meant that atoms left, uh, atoms that are left are the indices with 156, 7, 8, 9 for this one, right? So atoms, just give me a second, why this one is not writing? Yeah, this one. When I said from mass equals 994, this one atoms left from the indices, this one 156, 7, 8, 9 here. So this one to the values, this one to the indices, the values are for this indices, the values are 619, 21, 25. You can just check this one 27 and 30, right? 27 and 30, this is fine. So we have found the subset 1, 5 and 7 among this one 1, 5 and 7. This is fine. Now 157 contains the number, atomic number 6 plus 19 plus 25, that will lead to the 50. 50, right? Similar to this one 29, we have got the output 50 here. Right, so this is fine. We have got 50 again. When I say 50, these are C of 6, this one atomic symbols, right? So basically elements with the symbols, this one C of 6 plus K of 19 plus Mn of 25. This is fine, this is clear. I hope this is clear, man. Now we have to go with the subset mask, right? So what we have, the indices that we got here is 157. So this time we'll be going with the one left shift 1. So again 5 and 7, same thing we'll be performing. The values will be having 2 plus 32 plus 128. So this time we'll get the output 162 basically, right? So the last time how much we got here, basically just give me a second here, 162. So again after this one we'll be going with the next mask we have to go with, right? So this one previously we have got 29, I think, something, or 994. Next mask we will be going with the, previously we had got 994 basically here, 992. So this one 994, sorry, 994 XOR 162. So this we will get the value 832, right? So this time, previously DP of 1 and 994 we had set this one to the true. Now we have got the value 832 and we will be setting DP of 2 and 832 to true. So DP of 1 994 we have set this one to the true previously, right? So this time what we will be doing, we will be going with DP of 2 832, we will be setting this one to true. Simple, right? So parent of 2 832, so the value is 162. The value is 162, this one. Simple. Now we have got the value 162, right? So this is fine, I guess. Same thing, right? So previously we had got 50, sorry, 29, parent of 1994. Finally we got 29, right? After performing the XOR operation, 994 we got. So DP of this one we had set to true, and we have got 1994, that is equivalent to 29. 29 and 162 we got here now, right? So this is fine. Now we have r equals 2, right? So this is last one. So we had to consider for, what are the things here? Hmm, we are done with 39 by 50, this one SM, and finally we are with 78 PT, right? 78 nothing but PT. uh, symbol pt, right? So this is fine. Just give me a second here. Yeah. Now from mask we have previously we have 832, right? So first we had 994 from mask. The second we have what do we call 832, right? So just give me a second here. One second. One second. Yeah, first we had 994. Now we have 832. Now what we have? Um, Basically, we have found the subset 689. When I say again, when I say we have found the subset, so this one from mask 832 here, we have the atoms left. That is this one. We will be going with the remaining indices. The remaining indices left here are 6, 8, 9. So from 1 to 10 we have, right? So n equals 10 we have. So the remaining indices we have left here, we are left with the remaining indices 6, 8, and 9. You can just check in the input one, right? So I can just check in the input. So again, I have to go back and show. So I can just check the indices. This will be considering the remaining indices nothing but 6, 8, 9 with the values. So for this one, you can just check for the sixth one. The value is 21. For this, the value is 27. And for this, the value is 30. Simple, right? So we have found the subset, this one, 6, 8, and 9. So values are 21, 27, and 30. When we sum up this one, we will get 78. When we sum up this one, we'll get 78. Simple. Again, so what are these? 21, this one. We got 21, 27, and 30, right? So what are the atomic symbols basically? This one is Sc, Co, as well as the Saturn. 21, 27, as well as the 30. So we will be going with the, now the next is we have to go with the subset, this one, subset mask, right? So I have written subnet mask everywhere. This is subset mask. So sub, so what are the this one we got here, indices remaining 6, 8, 9. So one left shift 6, this one left shift 8 and 9, 6, 8, 9. So the values 64, when we do this, 64 plus 256 plus 512, you can just google it. So this is fine. Now we have got the output 832. 832. Simple. Let's move on with the further steps, right? So next mask we'll be going with the 832 XOR 832. So we will get 0 here. So DP of 30 will be set to true, right? So DP of 1, 994 we went with. So just give me a second here. And DP of 2, this one, 832 I think we went with, if I remember. Yeah, dp of 2 and 832, and dp of 3 and 0, as we have got 0 here, right? So we went with 832 XOR 832, nothing but the 0 here. So dp of 1 and 994 we have set to true first for the first one. For the second one, dp of 2, this one 832, we had set this one to the true. And finally we went with dp of 3. This time we have got the value 0 here, right? So this 0, again we'll be setting this one to true, right? So now we are done with this part. Parent 3 of 0, again 832. So what are the values that we got here? First one, this one I think, just give me a second here. For the first one, parent 194, we got 29. For the second one, we got 162, 29, 162, as well as the 832 I think, right? 29, 162, as well as the 832. Parent of 10, parent of this one, p of 10, I'll just write here. This one is nothing but the parent of 20, and this one is nothing but the parent of 30. Simple. 29, 162, as well as the 832. Now let's check the feasibility. So we are done with the sorted S2 part, right? So we went with 50, as well as this one. Let me come here. Just give me a second here. Hmm, 50, 39 by 50, as well as 38, right? So these three values we went with. This is fine, man. Now we are done with this part. So just give me a second here. Yeah, we are done with this part. So now let's check the feasibility. Feasibility in the sense we'll be going with the DP of K0, right? So K, we have the value 0. We have to, for the feasibility, we have to go with the K, right? So DP of K0 is nothing but DP of 30, right? So this is true. This is true, right? So initials, it has to be equivalent to the initial sum, if you remember the question, right? So what was our main goal, if you remember correctly? We have to obtain exactly k target atoms whose total sum equals to initial sum. So what we got here? 0. dp of k0 is equivalent to the dp of 30, which is quite obviously true, right? So now we have the answer, man. So ninth step is we will be going with a reconstruction. So this one I had mentioned first itself, right? So this reconstruction part was not required actually, but this is for printing the output, but we have to go with the, I have to show the reconstruction. So there is no other way, right? So we have to reconstruct nothing but the code reconstructs whatever the code that we write here. It reconstructs backwards starting from the mask when mask equals 0, right? So what we will do, we will start we'll start when mask equals 0, we'll be iterating nothing but r equals 3 to 1, right? So r equals 3 subparent 3 of 0. So the value we have 832, right? So we have the value 832 for parent 30, right? So we know this, right? Just now I had written somewhere 29 162 and 832, parent 10, parent of 20, parent of 30. I have written the value over here. Simple, right? So now we have the parent 30832. We have bits here. This one 689. We will be adding the element s1 of 6, right? So element s1 of 8, nothing but this co element, this one co element s1 of 9 is nothing but zn, right? So we'll be adding sc co plus zn, right? So this one this will print basically sc plus co plus zn. This is equivalent to the pt basically, right? So first one we got, so we got sc co and zn, nothing but the pt. So this is fine. So then what we will be doing, we will be masking nothing but the xor equals here I have made use of, right? So this one 162. So we that will lead to the mask, the value mask equals 994, right? 994. Simple. It's same thing we will be doing for r equals 2 to this one, r equals 2 and r equals 3. So we have went with r equals 1 here, I believe. Sorry, r equals 2, r equals 2. So now r equals 3, r equals 2, and r equals 1. Reverse we are going, right? So this is fine. So sub parent of 2 and 832 is 162 value. So bits again we have already got this one 157. So we have to add c plus k plus mn. You can just go to the video and check. So here 157 we are going with. So we have to add c and k and mn, right? So this we will be printing c plus k plus mn, nothing but this is equivalent to the sn, right? So this is equivalent to the initial sum, nothing but the sn, value of the sn. You can just check, man. It doesn't matter, you can just check. So then what we will do, well, mask xor that is equivalent to the 162. So this one mask equals 994 again, right? So finally we are left with r equals 1. Same thing, parent 1994 here, this one. So we have the value 29 for 1. We know this bits that we got initially was 0234. So I had explained this one. So this one we have to sum up li, f, mj, and p, right? So we can just this prints basically, we can just print li plus f plus mg plus p. This is equivalent to the y. Then we'll mask this one xor equals 29. So we'll be masking 1023. So basically this we got from these steps, right? So we did for dp of 1 this one until here, until here, right? So we did for 3 sorted s2s basically, for sorted s2s. Sorted S2 39 by 50 SN and 50, 78 PT. So this one itself, right? So now basically we have got all the values basically, right? So what are the things that are equivalent to the initial sum? Basically here I'll just come 1 second. So this one we have got SC plus CO plus ZN that is equivalent to the PT. So C plus K plus M that MN that is equivalent to the SN. And finally LI plus F plus MG plus P that is equivalent to the Y. Right? So now that we will be printing that one in the form of output. So the output that we got here is SC plus CO plus ZN that is equivalent to the PT. You can just check this one if you want. C plus K plus MN that is equivalent to the SN. So you can just check three of them, man. It doesn't matter, right? So c plus k plus mn that will lead to the sn, and finally we got li plus f plus mg plus p, right? Symbols li plus f plus mg plus p with atomic numbers that is equivalent to the y. So these three, k equals 3 we have, right? So k equals 3 we have. This is equivalent to the pt, sn, and y. we have got the correct output. SC plus CO plus ZN equivalent to PT, C plus K plus M1, and LI plus F plus MG, this one, SN and Y, equivalent to the SN and Y. Right, so what is the output they have mentioned here? Mn plus C plus K, SC plus Zn plus CO, Li plus Mg plus M. So you can just this one look into this one. So basically whatever the output that we got here is this one at the first, that is um, this one SC we have considered first accordingly, SC plus CO plus Zn. So this one they have given CO plus Zn plus SC. This is also fine, right? So ordering doesn't matter here, don't get confused, right? So we have Mn plus C plus K. Again, what is the output that we got here? Mn plus C plus K they have given here. So this one we have got C plus K plus Mn. So ordering doesn't matter. So this they have given second. Basically just give me a second, 1 second here. This stops writing, man. So this one they have given second, and this one they have given first actually, and finally this one they have given third one. So and ordering might differ, right? So they have given something SC at the last, basically Zn plus CO plus SC they have given. So here ordering we have got the order SC plus CO plus Zn, right? So it is equivalent to the PT, SN and Y. So this has to be same, PT, SN and Y. This has to be same, right? So just give me a second here. Yeah, SN, PT and Y, this has to be same. Yep. Now we have got the correct output. Now we have got the correct output. The output that we got is equivalent to the output that they have given for the example one within the question, right? So our approach works absolutely correct for this one. Our approach works absolutely correct, right? So now as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the what do we call complexities part, right? So what will be the time complexity here? The time complexity would be big of 3 into m into 3 to the power of n. So why it will be m into 3 to the 3 to the power of n? So again, I had said when we considered r equals 3, r equals 2, and r equals 1, I said we will be iterating r up to m, right, for each mask, and we will be iterating all its subsets. Subset sum we considered, right? So we iterate r up to m, and for each mask we iterate all its subsets. Nothing but sum over masks of 2 to the power of this one. What do we call? Pop count of mask. That will yield to 3 to the power of n, right? And one more thing, accordingly with the constraint or in the question they have mentioned, m is less than or equal to n. And this is also big O to the power of n into 3 to the power of n, right? So we can just consider big O of m into 3 to the power of n, or big O of n into 3 to the power of n. Both are right, right? So this is fine. So what will be the space complexity then? Space complexity would be m into 2 to the power of n. Why it will be m into 2 to the power of n, not 3? So we will be making use of the dp and parent that are sized m plus 1 into 2 to the power of n. This will be seeing in the code. Don't worry about it, right? So not to worry currently. So I'll just explain so that while writing the code don't get confused, right? So we will be considering the dp array and the parent that are sized m plus 1 into 2 to the power of n. Also, plus we'll be considering the subsum, right? In at every step we went with a subset sum, if you remember, right? So plus subsum of size 2 to the power of n will be considering. So overall space complexity would lead to big O of m into 2 to the power of n, right? So this is space complexity and this is time complexity, man. So time complexity is big of m into 3 to the power of n, and the space complexity is big of m into 2 to the power of n for the code that we'll be writing in the future, right? So I hope the complexities and the approach part is completely clear. As we are completely familiar with the approach and the complexities, we are good to write the code. And once more, I just want to tell you this: if you didn't understand anything, just please go to the video. Just you can just this one, go to the video where you didn't understand, you can just look into it again, right? So while writing the code, it will be necessary, it's necessary, right, to understand most of the things. So the code is lengthier, but it's very easy to understand if we go step by step, as we are going with the dp, right? As we are going with the dp, quite obviously we'll be breaking down the problems into sub problems and then we'll be solving. So we will be going with the pre-compute and other stuff, we'll be going with everything. So it's better if you didn't understand, you can just go to the video where you didn't understand, right? If you didn't understand anything, you can just comment, right? You can just comment in the this one, comment down. So I can just uh, tell you, right? I can just tell you whatever. If you didn't understand really, right, you can just comment down. So I'll just try to answer that, right? So this is fine. Now, as we are completely familiar with the complexity and the approach part, we are good to write the code. Let's start writing the code. So let's start writing the code now. So I'll just come here. Uh, let's do one thing. Let's import the classes for the fast input output, right? So as usual. So I'll just go with java dot input output dot star. So this is fine. Again, I'll just go with java dot util dot star. This is fine. Now let's go with the main class one, right? So I'll just go with, so you can just give any name for the class. I'll just go with, so this one, main. So within the main, first what we'll do, first step, if you remember, we have to map the atomic number to the element or the symbol, right? So first element goes H, second element goes H, E, and so on, right? So I'll just copy paste this one. So this one will be static string. So this one element, what we have done here, again, we are mapping atomic number to the element symbol, right? So that's what we are doing here. Simple. Let me let's move on with the further steps, right? So we have to consider n and m, nothing but the number of initial atoms, n, and m is nothing but the this one, what do we call, number of the target atoms. Basically m is m in the sense k, it is k, not the m, basically, right? So let's go with the m itself. Int n, sorry, oh, I'll just go with static here. Static, so this one will be int n comma m. Simple. Next step is, let's store the atomic numbers of the initial atoms. So accordingly with the constraint, n has to be less than or equal to 17, and we have to allocate 20. We had discussed this one, right? So in the question, we haven't discussed, but this one, constraints part. So this one will be s1. So this one will be new int of 20. So let me copy the same thing for s2 as well, right? Sorted s1 and s2, if you remember, right? So this one will be int, so this one will be s2 new int of, so this one will be 20. Simple. Now did I copy and did I just type? So David one, this is fine. Now let's go with the subsum of mask. I had explained, right? So this is nothing but the sum of numbers of elements that is included in the mask of S1. So we are going with the initialization part. I'll just go with int here. This one will be subsum. This is fine. Now we will be going with a boolean, dpra, basically. Let's go with the initialization rather than the explaining this one. Just go with boolean dp. This is nothing but dp of r mask, r and mask. So we can form first r targets leaving the mask atoms that are available. So this we know from the question. So now we are left with only parent. Parent of 10, parent of 20, parent of 30, we went with. Parent of 1994 we went with, right? After masking. Parent of 2, again with 832 we went with, I think, right? So for this one, 3470 and something, those three values that we got after sorted S2, this one, right? So the same thing, we have to consider the parent, right? So I'll just go with static here. So this one will be int, so this one will be parent. Simple. Now let's go with the main method one. So this is fine. Now let me go with throws exception here. So this is fine. Within the main method, what we'll be doing, the first step is, let's go with the input output part, buffered reader input, fast input, right? Buffered reader. So this one will be br new. So this one will be buffered reader new. So this one will be input stream reader. So this one of system dot n. So this is fine. Now m, sorry, we have to go with the output as well. Why did I consider m? This is fine, man. Print writer. So this one will be output, basically new. I'll just go with the print writer. So this one will be new buffered writer. This is fine. New output. This one will be stream writer. So let me go with the system dot out. This is fine. Now we'll be making use of the string tokenizer. We have to read the first line tokens, right? So I'll just go with here string tokenizer. I'll just go with st here. This one new string tokenizer buffered reader dot read line. So I'll just go with the read line. Now this is fine, man. Yeah. Now we are just reading the first line tokens. This is fine. Now we have to pass n and parse k. Nothing but n and m. In our case, for the k we have considered m, right? So I'll just go with n equals. So this one will be integer dot parse int. As it is integer, let's parse this one. Nothing but string tokenizer dot. Let me go with the next token here. Simple, right? Simple. Now let me assign m to this one will be integer dot percent. This is fine. So string tokenizer dot. So this one will be next token. So this is fine. We have successfully passed n and k. Now let's do one thing. Let's go with the hash map man. Means we have to map the symbol to the atomic number, right? So we have already considered element along with it. This one, what do we call symbols, right? So we just have to map the symbol to the atomic number now. For that, we'll be considering hash map. So I'll just go with the hash map here. So key and value it consists of, right? So this one will be string along with the integer atomic number, right? So integer. So this one I'll just consider MP or MAP. You can consider anything. I'll just go with the MP. So this one will be new hash map. Syntax part. Simple. We have successfully mapped symbol to the atomic number. So now we have to populate the map for the elements, right? So let's see. Now let's go with the iteration part. So this one will be int I equals 1, I less than or equal to 100. So this one will be fine. I plus plus. So this one I'll just go with the put operation that is provided by the hash map. So this one will be element. Let me pass the element of I, iterated value of the element along with its index I. This is fine, easy, right? So we are just going with the same thing, whatever that I have explained in the what do we call approach. We are articulating in the form of code, right? Now I'm just going with a count here. Let me initialize this one to the 0. Simple. Now let's read any initial element symbols possibly across the lines. I'll just go with a while loop here. While count less than n. So then what we will do within the while loop. So I'll just go with the if condition here. String tokenizer if it is equal to the null or string tokenizer. This one has. I'll just go with more tokens. So then what I'll do, I'll just go with string tokenizer equals new string tokenizer. So this one will be buffered reader dot read line. This is fine, man. Yep, simple. Now let me write the simple while loop here. Right, so this is related to the again string tokenizer has more tokens. So this one, and we have to consider count as well. When count is less than n, right? So this one we are considering when count is less than n. Then we have to get the symbol, right? First we have to get the symbol, meaning I'll just go with a string s here, s of the string, this one type string tokenizer dot. So this one will be next token. So let me go with trim here. So where is trim? This is not showing. This is fine. Trim. Sorry. So this one, after getting the symbol, so we have to go with the invalid symbol check, right? So let me write the simple if condition for that. So this one map. So let me make use of contains key here. Contains key of, let me pass the s here. So we are going with the invalid symbol check. So within this if condition we have to go with impossible input symbol. We have to print no in simple terms, right? So that is also one of the conditions that they have given in the question. So this one out, as we are considering the print writer, this one variable name out we have considered, right? So this one will be print ln. So let's print no, this we have considered in the question, man. We guys we should be knowing this one, right? So this is fine. So then we have to flush. So for that one, I can just go with a flush, or you can just go with a close as well. Out dot flush or close, both works. Either of them works, right? So this is fine. We don't have to return anything. I'll just give return here. So this is nothing but for the impossible input symbol. Now, let me come here. So we have to store its atomic number as well, right? So I'll just go with S1 here. So we have to increment the count, right? So this one, we have to store its atomic number, means we have to get the atomic number, right? So I'll just go with a map dot get what we need to pass, S, right? Simple, right? So we are done with this part. Let me come out of this one entirely. Now what we need to do here, I hope until here everything is clear, man. The code is really large actually, right? Let's go step by step as I've said for the code as well. Now we have to reset to target, to read the target symbols, right? So I'll just go with count here. Let me initialize this one to 0. String tokenizer, this one, let me go with null. So let me go with the while loop here. This one, count less than m within the while loop. So let me write the simple if condition here. String tokenizer, if the value is equivalent to null, or string tokenizer, if it has more tokens, nothing but has more tokens, I'll make use of here. So then let me assign string tokenizer or create the instance of it. So this one will be new string tokenizer. So this one will be buffered reader dot read line. So this is fine. Now let me write the simple while loop here. This one has more tokens, uh, and this is fine. Count less than n. Then this one has to be m, I believe, right? So k basically. K we have given m, not this one. Fine. First we have to get the target symbol again. Again we have to go with the invalid symbol check. Again we have to go with impossible input symbol. And finally we have to store its atomic number. The same steps we have to carry on. So I'll do one thing. Within the while loop, if condition. So next we don't have to trim anything over here, right? So string is, oh, we have to consider here as well, right? So this one we have to do. So let me do one thing here. We are doing this one for the S2, right? I should have copied the same thing, man, and made the necessary change, right? So this one, instead of n, we are considering m for the S2. That's all we are doing. So I'll just come here. Let me copy this entire thing. Just give me a second here. This is fine. Hmm, Until while loop I have written, right? So let me copy till here. This is fine. So this one has to be map, not mmp. So this is just mp we have considered for the map. So this is fine. So we are just writing from here, man. So this is also fine. String s. So this is fine. Now we have considered until here, right? So this is fine, man. Now instead of s1, let me go with the s2 of count plus plus. We are incrementing the count and we are just storing its atomic number here. We know this one from the previous step. So this is fine. We are done with this part. Let me come out of this one entirely. Right, now what we need to do, we have to sort initial atoms, right? So we have to sort the initial atoms, atom numbers basically ascending. Also we have to sort the target numbers ascending, right? So that is how we will match, right, in the particular order. So we have to initially sort the atomic numbers ascending as well as sort the target numbers ascending. So I'll just go with arrays dot sort here. So this one, let me pass s1 comma 0 comma and this is fine. uh Sorry, what did I just do? Let me copy this one and let me make the necessary changes here for this one, target in the sense s2. So this one, so this has to be m, nothing but the k. This is nothing but the target numbers, right? So target basically. This is fine, man. uh, Now what we need to do actually, if you remember the approach, after sorting after sorting was first itself, first step was starting actually, sorting. So after sorting, so we went with a bit mask, right? So now we have to go with a masking, nothing but we have to go with bit mask with n bit set, right? Nothing but all the atoms that are available we need to consider, right? So I'll just go with int here, full mask. So this one will be equal to 1 less than n. So this one minus 1. This is fine. Now what we will do, let's allocate the array of size 2 to the power of n for subset sum. So I'll just go with subsum here. So this one will be new int of 1 left shift n, right? So we have successfully allocated the array of size 2 to the power of n for the subset sums. Now let's move on with the iteration part, man. Let's go with the for loop here. Int mask equals 1. So this is fine. Mask less than or equal to full mask. So this is also fine. Mask plus plus. So what we are doing here, we are computing the subsum for every non-empty subset. So that's what we did, if you remember the approach, right? So now we have to go with the least significant set bit of mask, as we are trying to articulate the approach thing in the form of code here. We cannot just write it in the form of this one, right? English or whatever the language that we know. We have to articulate that one in the form of code. Now let's go with the least significant set of set bit of mask. Also, let's go with the index of that particular bit, nothing but zero index, right? Zero based indexing. So now let's do that first. Least significant bit, I'll just go with LSB here. This one, mask, bitwise and hyphen mask. Simple. We are just going with a least significant set bit of the mask. Now we are going with the index of that particular bit, nothing but zero based, right? So I'll just go with the index idx. So let me assign this one to integer dot number of trailing zeros I want to make use of. So this one will be number of, so this one will be trailing, this one will be zeros, right? So let me pass the least significant bit. This is fine. So now we have went with the least significant set of bit set bit of mask. Also we went with the index of that particular bit, nothing but zero based. Now we know this one from the this one, what do we call from the approach, subsum is equivalent to the subsum without the least significant bit, or subsum equal to the subsum plus the value at that particular index. That's what we did in the approach basically. So the same thing, let's articulate in the form of code now. So subsum at the end of each step, right? So we went with r equals 1 2 and 3, if you remember the subset sum, right? That subsum we are considering now. Subsum, so mask, this is fine. So this one will be subsum of, so let me go with the mask here. We went with the xr, if you remember. So I'll just go with least significant bit again. So we have to go with the s1 this time. So let me pass index. So this is fine, man. Simple. We are done with this part. Let me come out of this one entirely. Now let's go with the DP. Now we went, I showed you the masking part, now bit mask part. Now let's go with the DP. Nothing but, so we have to consider the DP rows from 0 to M, columns for all the masks, right? So I'll just assign DP to new. So let me go with Boolean here. So this one will be M plus 1 along with 1 left shift N here. This is fine. Simple. Now let me go with the parent here. Let me assign this one to new int of m plus 1. Simple. So this one will be 1 left shift instead of this one. So we have to go with n again, right? So this is nothing but the parent. So parent to reconstruct the chosen subset for each state. If you remember the step 9, we went with the reconstruction, right? So that's what we have to consider the parent for that. If you remember, parent of 1994, parent of 1382, parent of 30, right? The values that we got, if you remember, right? The same thing. We are making use of the parent to reconstruct the chosen subset for the each state. Now let's initialize the parent with -1, right? If meaning if we don't have the parent, then we have to initialize the parent with -1, right? So let me go with the for loop, nothing but the iteration part here. int, this one will be row, so row of parent. So this is also fine. Now I'll just go with arrays dot fill. So this one row comma minus one. This is fine, man. We are done with this part. Now let's do one thing. Let's go with the this one. Mask, full mask part, nothing but dp of 0 full mask. We have to set that one to true, if you remember the approach, meaning we are going with the base case here, right? So before making any target, all the atoms should be available. That is the base case. We are setting this one to the true, so meaning here dp of 0, I'll just go with the full mask here, this one. Let me set this one to the true. Let me set this one to the true. Simple. Now let's go with the iteration part. Right. So this is big headache, man. So many nested loops. Actually, we have to go with, right. So we have to go with the R, we have to go with the sub, and also we have to go with the this one, a mask as well. So first, let's do one thing. For each target index R, let's go with the zero based in sorted S2. Right. So accordingly with the approach we are going. So here this will be int R equals 0, R less than M. So let me increment the R. So within the this one, this loop, so we have to go with one more for loop, nothing but for every possible mask of this one. What do we call remaining atoms? We have to consider, right? So in simple terms, we will be going with a one more for loop. So I'll just go with for here and mask equals 0, mask less than or equal to full mask. So this one will be, let's increment the mask. So this is fine. Now let's go with a simple if condition. If not of dp, so this one r, so this one mask, then what we need to do, we have to skip. So in the this one approach, I said we have to skip the unreachable states, right? So here the same thing we are doing. We will be skipping the unreachable states, yeah, but in the form of code. For skipping, we can just make use of the continue keyword, right? So I'll just go with here continue. This is fine. Now let me make use of one more for loop here, because we have to iterate all the non-empty subsets of the mask as well. We have to do that as well, right? So we have to iterate all the non-empty subsets of the mask. So again, one more this one. What do we call? Let's go with one more for loop, man. Just give me a second here. Did I do anything wrong? No, right? So yeah, let me go with one more for loop here. This one will be int sub. This one, let me assign this one to mask. So sub greater than 0. Let me set the sub equals to sub minus 1. And let's make use of the bitwise AND operator. Let me pass mask here. This is fine. So within this for loop, what shall we do? So we have to go with simple if condition, man. Meaning if subset sum is equivalent to the current target number, right? So then we have to remove those atoms, nothing but, and then we have to move to the next mask. So before writing that, let me explain this one step by step. First, let's go with a simple if condition, meaning if subset sum equals to current target number, right? So I'll just go with if we have considered sub sum here. This one, let me pass sub. This is fine. If it is equivalent to sorted S2, right? So this one is nothing but the S2 of R. So this is fine, man. So if the subset sum equals current target number, then we have to remove those atoms uh, to move to the next mask, meaning int this one next mask. So this one will be mask uh, x, or so this one, let me give sub here. This is fine, man. Let's go with a simple if condition. If we haven't already reached this particular state, then we have to mark this one reachable, right? So then we have to mark reachable and store which subset formed the this one. What do we call rth target, right? So that's what we need to do. The same thing we have to write in the form of code. Let's write that one, man. So this one, if dp r plus 1, this is fine. Let me pass next mask here. This is also fine. So within this if condition, what we will be doing, so we have to mark this one unreachable, right? So this one I'll just go with dp of r plus 1. This is fine. Let me pass the next mask as well. So let me set this one to the true. Finally, we have to store which subset forms the r target, right? So again, that one, if you remember the parent part, so I'll just go with the parent of r plus 1 here, parent of 1, this one 994, as I've said, that one. So we have to go with the next mask, right? So this one we have to assign this one to the sub. Simple. Exact same thing whatever we discussed in the approach, the same thing we are articulating in the form of code. I stressed this one multiple times. Please listen to the approach, right? So if you are confused about anything, please do go through the approach once, right? So you can just go to the previous part of the video where I have explained this one, and then you can come here. You'll understand this one clearly, right? So this is fine. We are done with this part, right? So I'll just come here. It's fine. Let me come out of this one entirely. Now we are left with certain things. Let's finish up. Let's finish this off soon. Now, if after forming the M targets, we don't end with N, we don't end with no items left, nothing but impossible. Meaning, so if it is not possible, we have to return no in simple terms, man. So I don't want to tell the story here. This is fine. DP of this one M 0. So this one will be out dot println. So this one, let me print no here. This is fine. Now let me go with the out dot flush again, or you can just go with close. Either of them works. You don't have to return anything. Let me give the keyword return along with the semicolon. Right. So we are done with this part. Almost we are done. So if it is possible, in our case it was possible, right? From the sorted s2 it was possible for the reconstruction, right? So if it is possible, then we have to reconstruct the solution. So in that case we have to print s. If you remember, see here, before printing this one, what do we call, what are the, if, whether it is equivalent to the initial sum or not, we have to print all the symbols, right? So plus this one we went with ptsn and finally, right? So before printing that one we have to print s if it is possible for the reconstruction, right? See here, s. So that part, let's write that part first. So I'll just go with out dot, let me go with the println here. So let me give s here. Simple, right? So now let's do one thing. Let's initialize mask to 0. This is fine, nothing. Meaning here we reconstruct backwards, in the sense we are starting from the mask that is equivalent to the value 0. No items remain after all, right? So here we are starting from the mask that is the value 0. Just remember this one. Now let's move on with the iteration part one. So this one will be for int r equals m, r, this one greater than 0. So this one will be r minus minus. Simple. We are iterating the targets in the reverse order. Now let's go with the subset that is used to reach the state. Nothing but in the approach, if you remember, we went with r comma mask, right? So this one we can just articulate in the form of code in this way. Int sub equals, let me give parent here. So this one will be parent of r. Let me pass mask here. Simple. Now let's do one thing. Let's go. We have to go, not let's go. We have to go with the corresponding target number. We have to go with the corresponding target number. Nothing but r minus 1 becomes s2, right? And s2 is 0 based. We know this one, right? So let me go with the target variable name. Yeah, this one will be s2 of r minus 1. This is fine. Now let's collect all the symbols that we have used for this particular target. So let me go with the list here. So this is of type string, right? So let me pass string here. So let me go with the variable name part. So this one new, I have to type completely RLS. This is fine. Syntax. We're done with this part. Now let's do one thing, man. Uh, we have collected all the symbols that is used for this particular target, right? So now let's go with the iteration part. Nothing but simple for loop. So this one will be int I equals 0, I less than n. So this one will be I plus plus. So within the for loop, what we will be doing, let's go with a simple if condition, meaning if bit I belongs to the subset, so then what we need to do, see here, if, so this one is fine. sub. So this one, right shift I, and let me go with bitwise and 1. So this is fine. So if the value is equivalent to 1, then meaning here, if the bit I belongs to the subset, then we have to add the original symbol for that particular atomic number. That's what we did, right? So how can I write that one? So I can just keep here parts dot add. So this one, let me go with elements here. This is fine. Elements of, so this one, if you remember, s1 of I. Uh, this is fine, man. Let me give semicolon here. Let me come out of this one entirely. Finally, what we need to do, we have to print the equation for this particular target. So let's see how can we write that one in the form of code. So I'll just give here out dot println. This is fine. Let me go with string dot join here. This is also fine. So let me go with plus here. So let me go with parts as well. This is fine. Again, let me append certain things here. So let me go with a arrow mark here. This is fine. So arrow mark because here we need to print in this way, right? I mean this one element symbols along with this one here. See arrow mark this one. So this has to be equivalent to the particular element, right? Element symbol. So this one arrow mark is fine. Then we have to append. What we need to append? The target element. So this one is nothing but element. So within the array we have to pass the target in the form of code we are writing, right? So this is fine. Now finally we have to go to the previous mask, nothing but we have to undo the XOR. So here this will be mask XOR, so equals sub. So we are just going to the previous mask, nothing but we are undoing the XOR, right? So this is fine, man. Finally, let's flush the output. So this one will be out dot flush. We are done with the coding part. Somewhere I have messed up. What I have messed up, I don't know. So out dot flush, we have to get one. We have to get one more bracket here. So what did I miss? I don't know here. Mm, this is also fine, man. Subsum of mask. Fine. S2 of count. This one also fine. Dot println. This one is also fine. S1 of count. This one is same as this one. This is also fine. Um, somewhere I have messed up something. I don't know where I have messed up, but I have messed up something. The code is huge. Anyways, uh, let's do one thing before checking the this one code with a different this one inputs. So let me copy paste the signature starter template, man. Just give me a second here. 1 second. So let me come here, paste this one. Let's check what is the error that we'll be getting. So let's do one thing. 1 second. So let me come here. Let me copy this one. The output that we need to get here is this one, right? So order doesn't matter here. Anyways, expected semicolon here. Line number 63. So let's do one thing. Just come to 63 here. So this one count equals 0. This is fine, man. St equals null. Yeah, this we have to give semicolon here. While passing, reached end of the line while passing. So this one more lar bracket. Oh, we have many errors, man. Yeah, 9 errors. So while count cannot find the symbol where I have initialized count. Oh, count. Oh, I have given COUNT here. I have used CNT everywhere. So now this error has to be gone. Yeah, we are left with 2 errors actually. Uh, cannot find symbol elements. We had made use of the element, right? So why did I give S here? Elements I have given line number 122, man. Where is this line number 122? This one. Yeah, let me remove s here. So because we are making use of the element, not the elements, so this is fine. We know this one. Now, yeah, we are left with only one error. Again, I have made use of the elements. I have to go with the element one. So this one, yeah, now we are getting the correct output. See here, the order is different. Order is different. So we are getting this one, c plus k plus mn. So f plus z and this one y, as well as the this one li mg p plus sc plus co. So this doesn't matter. So we have got this is equivalent to pt sn and y, right? So this is fine now. Now let me check with this one. Maybe we might get the different answer. So we are getting h plus h, this one he, right? H plus it, this one equivalent to the he. Correct. This one we are getting this output itself, right? So we can have the multiple outputs, right? So this is fine. Now let me copy this one. We have to get the output no. I hope we get the output no for this one, man. Yeah, we have got the output no. This works correctly. Let's see. Let me copy this entire code. So let me come here. Let me hit the submit code button. We come to the submission part. This is E, right? Problem E. Yeah, nuclear fusion. So let me paste the code over here. Let me hit the submit button. I hope this works for all the test cases. Let's see. So this is the code is somewhat lengthier. I don't say no. The code is somewhat lengthier, but very easy to understand, man. Right? So all we have to do is break down this one, break down the problem or break down the solution part. So you can clearly see here we have got accepted in the toast, right? So this is fine. So we have to break down the problem correctly, or the solution. First we have to break down the problem and try to understand what we have to do. Then in the solution part we have to break down this one, whatever we are writing, the code that we are writing, that we have to break down correctly, and then we have to write the code. That's it. The main thing here would be masking as well as making use of the dp properly, right? So that is the main thing. Basically we went with the sorting, masking, as well as the nothing but bit mask dp, right? So these two things we have to keep in mind along with the pre-computing the values, right? So along with the masking. So I hope this part is completely clear, man. So I can clearly see here the verdict that we got here is accepted, right? So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.